So next up, what we're going to do is try to actually graph some equations, and we'll be changing all of these different pieces, the amplitude, the period, all of that kind of stuff. To start with, though, let's just talk about what the sine and cosine functions will look like in general. So in general, we just say f of x equals, we're going to use some different letters here. So there's my sine function, there's x, and then I have a, b, c, and d in here. So let's go ahead, and I'm actually going to color code each of those, but just so you can kind of see what the final product will look like. So we'll use blue for A, green for B, yellow for C, and then red for D. Similarly, we might have a function for cosine, and cosine really, well, sine and cosine are really the exact same. They've just kind of been shifted away from each other. So I have, again, A, B, C, and then D. And here's what each of them stands for. So that first letter A is the, okay. It'll be easier to read it. Okay, A is the amplitude, whatever it might be. Technically, A could be negative, so you really want the absolute value. Amplitude can never be negative. And if you're thinking about transformations, this would actually be a vertical stretch or shrink. And so this is what's sort of squishing it or increasing the height of those waves. The next number we have to look at is B. Now B is related to the period. B actually equals 2 times pi divided by P, where P is the period. So B is not the period. It's really important to notice that. But it is how you would find the period. We could also rewrite this equation by solving for P, depending on which one is more useful. So sometimes you'll want to solve for B given the period. You might use the first form, or you might want to solve for P given B. It just kind of depends. And so in this one, P stands for period. Next up we have C. So C is the phase shift. And so going back to our transformations, this is a horizontal translation. By the way, I should mention up here that B is the horizontal dilation, stretch, or shrink. And that's why the period is actually adjusted by 2 pi over B, because it's originally 2 pi, and then you divide it by B to stretch it or shrink it accordingly. Finally, we have D. So D is the midline or the average value, and this is the vertical translation. Okay. All right, so now we're all set to actually solve some problems out. So what we'll do is, let's just start off by, let's call this an example. So identify the features of the following functions. So we're not actually going to graph yet. I just want to do some practice with identifying these features. So let's start off with y equals 1/2 sine of 4. Let's go with x. Let's just call it x for now. We won't worry about the phase shift. Sorry for the typo there. 4x, and then we'll just go ahead and subtract 7, for example. All right, so let's start off by identifying the numbers that are changing stuff. That is the A. Then this 4 is going to be B. C is just 0, so there's no phase shift. And then finally this -7 is D. So to answer this question, you would say the amplitude equals 1/2. B is not actually a feature of the graph. I never care really what B is. So you'd actually want to figure out what the period is. So when I'm asking about key features, I'm really asking about the period. So you'd say it's 2 pi over B, which reduces to just pi over 2. And then finally the midline would be y equals -7. I guess we should also put the phase shift on here, so we'll say phase shift is just 0, so there's no phase shift. And that's it. So you're just given an equation, and then you just have to pull out the key information from there. I realize I put part A, but really I think I'm just going to do one example. Okay, so this first example is just useful in helping to identify the key features. Now let's go ahead and actually graph some equations. So we're going to graph the following. This time I will do more than one. So let's start off with cosine. So I'm going to write graph y equals cosine of, let's do pi over 2 times x plus 1. And then let's go with -3. All right. So first of all, notice that there's no number here. That means that the amplitude is just 1. Second of all, we're going to notice that this is my B value. So let's go ahead and find the period. The period is 2 pi over 2, which is 2 pi over 1 times 2 over pi. And so the period is actually just 4. So we've kind of left our pi mode, and now we're just going to write the period equals 4. The phase shift is here, but actually this is -c. We want this to be, even though it's +1, it's actually going to be 1 to the left. And then finally the midline is going to be y equals -3. Okay, let's put it all together. Now, step 1, I always adjust the amplitude and period first. And by adjust, I mean that what I'm going to do is I'm actually going to put the period, which is 4, I'm going to put that on my graph first. 4. And so when I'm saying adjust, what I'm really talking about is scale on my axes. The amplitude is 1, so I can just go up to 1 and down to -1 still. And then I'm going to break up this x-axis into equal parts, just like I did in the previous video where we had 2 pi, so I went from 0 to 2 pi, and then I broke that up, and I said something along those lines. We're doing the exact same thing here, except that it's just 1, 2, 3, 4. Okay, and so now all I have to do to graph my function is take a look at, okay, it's cosines. That means I'm going to start up here. And then every single cosine graph does this. On one full period, it has to start up, come back down again, and then curl back around like this. And so I know that it just goes from 1, so the y values go 1 to 0 to -1 to 0 again to 1. At each of those key points, just going around the unit circle. Okay, so I have adjusted my amplitude and my period. Now the next thing I have to do is actually shift things around. So I'm looking at my information here. I have to move it 1 to the left, and I have to shift the midline to be at -3. So let's go ahead and rewrite this since I didn't quite plan ahead. So we have y and x. I need my midline to be down here at -3. So what I like to do is go ahead and just draw sort of a dotted line there. My axes I adjusted in the previous part, so I already know that I'm going to go 1, 2, 3, 4. From the midline, I go up 1 and also down 1. So we're going to have to go up 1 to -2 and down to -4. I'm also going to have to shift it to the left 1. So that first point here, this point is at currently 0, 1. That's going to go left 1 and then down 3. So it's going to be right here. And then you could do this process if you'd like with all the other points. So this next point would be 1, 0. If I go left 1, it's going to be 0, and then down 3 will be -3. Or you can just notice that we have our pattern again. So cosine starting up, it comes down, it goes back up again, and then that pattern repeats itself. And there you have it. So I've just sketched my cosine graph. Once again, I first adjusted my axes, and then I just shifted it around to get where I needed it to go. Okay, let's go ahead and try another one. So let's do y equals, let's go with 1/2 sine of 2, and then it's going to be x minus pi over 4, and then let's go with plus 3. No, I already did a 3. Let's go plus 5. Okay. So once again, I'm going to go ahead and just find my amplitude. I'm going to start going through this a little bit more quickly. The amplitude is 1/2. The period is 2 pi over b, so I end up with just pi. The midline is y equals 5, and then the phase shift ps is pi over 4 to the right. Okay, so step 1, I'm going to go ahead and adjust my axes. My amplitude is 1/2, so I know that I only need to go up to 1/2 and -1/2. I can still include the 1 and the -1 if I want. And then my period is pi, so we'll go ahead and put a pi there, and then I'm going to break this up. So half of pi is pi over 2, half of pi over 2 is pi over 4, and then I know this one is going to have to be 3 pi over 4, because each of these segments is pi over 4, and there's 3 of them. That's basically how it's always going to work. Okay, so that means that my graph now, remember sine always starts here, so I'm going to start there, go up, come back down, hitting each of these points that I've picked out. So by setting my scale on my x-axis, I sort of set up the entire problem because I know those are the key points there. Okay, so once again, the graph of sine always looks the same, it's just the scale that's going to change. Okay, now we have to shift this up 5. So let's go ahead and do that. I'm going to go up here to 5, and let's say this is 5.5, so 5.5, and then let's say this is 4.5, because I'm going up and down by 1/2. I'm going to put my midline in there, and then just to make sure my axes are correct, I'm going to do one of these squiggles here to show that I sort of broke the y-axis, and I'm not going to scale until I hit that line up there. Okay, then on my x-axis, I still need my pi over 2, my pi over 4, my 3 pi over 4. Notice I am leaving myself a bit of room to work because when we shift left and right, we'll have to adjust some stuff. Okay, so then I'm going to be shifting to the right, so I'm probably going to want this point. Looking at the pattern, it looks like it's going to be 5 pi over 4, or you could just do pi plus to get that next point. So let's go ahead and graph. So this point that's right here at 0, 0 has now shifted to the right and then up 5, so it's there. And now we can just continue our pattern. You can see why the midline is nice, why I put that red line there. Because it kind of helps me anchor myself, and it helps me know where those 5 special points go. And so there would be my graph of sine. All right. Now before we switch gears and talk about how to find the equation if you're given a graph, we're actually done graphing. I'm not going to be doing any more with that. We'll next be talking about how to get the equation if you're given a graph. Before we do that though, I want to go ahead and show you how you might do this in Desmos and talk about a couple of common mistakes. All right, so let's go ahead and graph y equals, and then I'm going to use my common functions here and do sine of x. And by the way, if you look at your Desmos testing one, you can open up a Desmos testing, you'll notice that you actually can graph it on this one as well. And we'll talk about why it looks weird in just a moment. Okay, so here's my graph of sine. Notice that it gets to pi over 2 is when it hits its max of 1. 3 pi over 2 is when it hits its minimum of -1, and then it has these other special points that we graphed. Now, the axes can be adjusted to make it look a little bit nicer. Let's go ahead and graph y equals cosine of x before we do that. So here's y equals cosine of x. Same sort of thing, right? It starts at its max, and then at 2 pi it's at its max again. All right, so I'm going to click this little, so over here you should see on the right a home button, a minus, and a plus to zoom in and to zoom out. Above that there's sort of a tool icon. I'm going to click on that and it opens up the settings. So there's a lot you can do here. You can change the grid, you can change it to a circle, which you might wonder why you want to do that, and we'll talk about that later. You can change some other stuff. But what I want to look at down here is where it says x-axis. I can change the step to be pi. And so now when I look at my graph, notice how I have pi, actually I have all these points lined up. You could even change the step to be pi, and then I'm going to write divided by 2. And so now it actually is going to look a lot like the graph we made. Now everything lines up nicely. Rather than what it was before when it was just going up by, oops, oh, it's not working, there we go, going up by ones, right? So then it doesn't quite line up, but you can change it to be pi. Okay. And so then let's say I wanted to graph my function, where was it? This one here, for example, 1/2 sine of 2, etc., etc. Y equals 1/2 sine of 2x minus pi divided by 4. Close those parentheses out and then add 5. You'll notice here is my graph. So I have my mins and maxes, 0, pi over 2, and then at pi. So if we take a look here, we should sort of see the same graph, although Desmos looks a bit nicer. But that's how you could graph it. Great. Now I want to go back to that Desmos testing, because you'll notice that this graph looks really bad. Although if I zoom out, let's go ahead and let's just zoom out on the x-axis. So I'm going to just pinch the x-axis. Notice that when I pinch out, it actually doesn't look so bad. The reason is because this is currently graphing in degrees mode. So let's go back to my original Desmos here. If I change the settings to degrees, notice I get that same graph. So degrees gives me the same one I started with in the testing mode versus radians. So degrees, your period is actually going to be 360. So if you wanted to, also it's just kind of fun to zoom in and out, but if you wanted to see a complete graph when you're in degrees mode, you would have to zoom out. And now of course my X scale doesn't look so good. But you'd have to zoom out so that you were at 360 here. And now it does look like a sine function. It kind of looks like what we started with. Because I originally said, oh, this is way back. I originally said if we're graphing from 0 to 360, it does look like a sine function. But remember, with pi is only 3, and 2 pi is only 6. So you're a long ways from getting to 360. So one really common mistake I see, especially if you're using a TI-84 graphing calculator, is students will forget they're in degrees mode, and then when they go to graph something, it'll look weird, and they'll be really upset about it. Okay, but that is the final item I wanted to show you in this video, how to use Desmos, and also keeping in mind that radians and degrees. And also you can use Desmos on your ACT or other standardized test.